Yeah, so in last class we have discussed about the functional programming language. The basic data types, as we have discussed, only are majorly two: items and lists. Lists are your data structure, linked list kind, structure it is. And then we said list consists of set of items, atoms. Atoms could be digits or alphabets or strings or any kind. So we have started with the scheme, which is generally being used to teach at the academic level for functional programming languages. Where if you can see, it is a typeless language. You need not to mention the type. Automatically, the type will be taken care based on the context. It means the value that you have passed for the atoms, right? And we have seen the two basic, programming concept that it follows is one, the referential transparency. Another one is the tail recursion. So we have seen those things in detail, and we have then seen the basic operations on list, like cons, car, CDR, using which probably you can have different operations can be implemented, such as searching, sorting, and appending the list, and performing Lisp, and ML. Then we have seen, their programming concepts and the way the syntax is being differed. Otherwise, the concepts are very similar in all this programming language that we are seeing, right from scheme. Scheme, as I said, one is the dialect of Lisp. And then Lisp is first functional programming language, common Lisp, which is being widely used across the commercial sector. Fine, and this is interpreter based, as we discussed. Then ML meta language, which we said is also the functional programming language, using the same programming constructs and the concepts. Only thing is it differs with syntax and all that we have seen. And coming to Haskell is another functional programming language we probably discussed today. It is very similar to ML from syntax and static scope point of view. It is strongly typed, and type inferencing and pattern matching. All this which we have said that ML is inculcated with, the same Haskell is also having all such kind of programming concepts. Syntax also, if you see, it's very similar to that of ML. Okay. And it is static scope in the sense when you declare a particular variable within a particular block in which it is accessible, fine. And if you are trying to access it outside of the block or in any other block, you cannot access it rather, right? And it is strongly typed. It means that the type of the data has to be mentioned clearly, okay? And then type inferencing, you can probably inference the types from one to another. Pattern matching option is also available, where probably when you're writing the functions, if you have multiple conditions to be checked. So looking at the pattern parameters that you pass to the particular function are being compared across the different options that are available in the definition to get the respective code to be executed, right? So it is different. How it is different from ML is it is purely functional and no variable, no assignment statement, and no side effects of any kind. Okay. So now we can see the syntax of Haskell here, a bit of the same. Let us look at this particular example here, factorial of a number. So fact followed by 0 equal to 1, and fact n equal to n into fact of n minus 1 here. So the parameter that you have passed to the function here is 0, here is n. So if the function is called with the parameter 0 value, it returns 1. If you have passed the parameter value as n, then that has to be, that has to invoke this particular code, right? So the code which you have will pass the parameter value n is nothing but n into fact of n minus 1. Okay. So it means, a recursive kind, code is available here when the value is not 0. So here you have n into the value whatever you pass for n, that into then, and then again that same fact function is going to be called by passing the n minus 1. So that n minus 1 value which is being obtained through is 0, then it returns 1. Otherwise, again it comes here, which recursively implements until you get the value 1 when the parameter get compared with 0. Right? Fibonacci series. Fibonacci series is basically starting with 0, 1. The subsequent numbers, you find the sum of its two predecessors rather, right? So you can see the recursive definition of the same is here mentioned. If the value of parameter is 0, it returns 1. If it is 1, it returns 1. Fine. Here, if it is not among 0 and 1, then it invokes this. There you can see the n plus 2. N plus 2 is of course the successor of n plus 1 and n1, right? So how do you evaluate the value in the Fibonacci series? By getting the sum of its two predecessors. So the predecessor of n plus 2, two predecessors of n plus 2 are n plus 1 and n. So which are going to be added, right? So you can see the definition here. Here you can see if you have multiple options where the multiple options been defined separately in this case, but if I want to combine together into a single one with the help of pattern matching, we can go and very similar to that ML, we can write here. You can see factorial of n the program the function before modified with a bit here with the help of pattern matching approach. So you just pass the value for n here. Then if the value is 0, it returns 1. If it is greater than 0, then it writes n into factor of n. So these conditions are going to be taken care with a single function here, right? So based on the value that you have passed to the parameter, which is going to be compared for the first option. If the first option is found to be true, or the first matching is done, then it returns this. If the first option is not matched, then it goes to the next matching, right? So with the help of vertical bar, you can separate the options if you have multiple options to be defined in a function with the help of pattern matching, right? Similarly, another function is mentioned here, where if you want n less than 100, if n value is to return 0, if n value is greater than 100, you want to return 2. So devise your code accordingly. You can probably write here, separating it with the vertical bar here, right? So, like for example, if I have a function like the square of x equal to x into x, it's going to give us the value of sum of the value that you pass, right? It works for any numeric type of x value, right? So if you look at list operations that we perform in Haskell are again very similar to that what we have seen in before languages. Like I want to find the length of the direction. How do you find? I have a symbol called hash. If I use that, it gives me the length of the list, okay, which has written user for, right? If I want to find the arithmetic series, we have a symbol called dot dot. For example, a list carrying more number of elements, but we want to represent only short form of the same, so we can use this dot dot 10. So if I have a list like this 2, 4 dot dot 10, it means from 4 till 10. By applying the formula that has been used here in order to generate the elements in this particular list. So what is the formula? It is the difference of 2 rather, right? So every element is difference of 2. So of its predecessor rather, right? So so if I have 2, then I have 4, then probably the subsequent I add 2 to its predecessor, right? So that way probably I can generate the values in the list, right? So if I have instead of having to represent the entire thing, I can just say dot dot, right? If I have till 100 also, I can just say 2, 4 dot dot 100. Instead of writing 2, 4, 6, 8, 10, 12 and all kind of thing, right? You can cut short it with the help of this dot dot, right? If you have a kind of series, fine, any arithmetic series, right? And if you want to concatenate, concatenation will do it with the help of cons operation, right? So similarly here we have a symbol called plus plus, fine. So you can use plus symbol. So this plus symbol is going to concatenate 1, 3, you have a list and you have another list 5, 7. If I want to concatenate this, I just say plus, so it concatenates. When it concatenates, you can see 1, 3, 5, 7 together in a single list. You get the results. Fine. Cons, scar, and CDR. You can implement these operations here with the help of colon. Cons is implemented with the help of colon, right? So cons is equivalent to colon here, and car and CDR. Car is content address register, content decrement register. So content address register will give you the what do you call head, right? So this is a list. In this list, what is head? Head is nothing but 1. So you can represent like this. 1 is your car generated output, and the remainder part is of course a list kind having the remaining elements, right? Which is with the tail part of it, right? So the CDR result is nothing but your tail part of the same, right? So finding the factor of the same with the help of product. If I am using here another function called product. This product is a function which will give you the product of all the elements available in the list, right? So let us say factorial of n, right? You can you know that factorial of n to be found, the elements starting with 1 till n. 1 till n have to be multiplied with all, so that you get the result out of it is nothing but the factorial of that number, right? So you can use this arithmetic series approach and define another function product. So this product function is basically finding out the product of the list, right? Product of the list. You can see here when you pass the list. For example, here I am passing product of 1 to n. 1 dot dot n is from 1 till n, all the elements. So for example, if n value is 5, so 1 till 1 dot dot 5 is 1, 2, 3, 4, 5 will be passed. If it is initially when you find this is not true because it's not null, so it comes here, then it represents in the form of cons. This is cons operation, right? Cons, this is CR operation. This is CDR operation. So car, cons, CDR operation. So we have represented the list in the form of car, cons, CDR, right? So then what do you get now? Here you get obviously 1 here, because in 1 to 5 you have 1 here, then colon, then you get the list as 2, 3, 4, 5, which is going to be sit inside the code. Inside the code, when you go A into means 1 into, then product of X means remainder part will be sent. So remainder is still not null, so it comes here. So it will be represented again in that form, then it will be 2 is to 3, 4, 5. Then when it is sent inside the loop, it is 1 into 2 into, then you send the remainder part, that is 3, 4, 5. So it takes the remainder part every time when after the head part is being multiplied to the accumulated product, and then the code is going to be executed until you get the null value. When the null value is reached, it means when all the elements of the particular list are being multiplied with accumulated product, right? Then what will be written here? It will return you what? It will return you 1, right? So that 1 is going to be multiplied, right? So the product of all this is nothing but 120 will be returned. Is nothing but the factorial of the same, right? So this is how as well you can, either if you want to implement factorial of the same, which we have seen before, with the help of this arithmetic series approach as well, right? This is an iterative approach. Got it? So this is an iterative approach. The one which we've seen before is the recursive approach. This is the recursive approach. So, and this is the pattern matching approach of recursion, and this is your iterative approach. This way you can probably implement having these two different kind of approaches while implementing the programs with functions. List comprehension. Use the elements of a list as a set as well. You can the sets are being represented with the help of braces in mathematics, right? So the kind of operations that you perform, all such operations you can perform here by defining the code for the same, right? Union, conjunction, union, intersection, and Cartesian products and minus and all kind of thing, right? So if you want to, let us say, for example, find the list of squares of first 20 positive integers, you can write the code like this: n into n. Here you are saying that where n is going to get the values from 1 to 20. So taking n values from 1 to 20, you are finding the square of all such will be produced as a list here, right? So you can write function like this. All of the factors of its given parameter, if you want to find, you can probably define the function like this. Factors of n. You want to find out all the factors of n, which is going to be generated as a list here. So the list carrying I elements, where I is going to get the elements from 1 to n, where these elements are divisible of 2, and you can say that I is only a factor of n when it divides n perfectly. It means n mod I should be 0. So when this condition is true, only then this I value will be taken into the resulting set, resulting list. That way the list is going to be generated carrying all the factors of n. Okay. Now coming to quick start logic, you must have read in data structure. You have a pivot element or the key element, you call it as, which is generally the first element. You consider, right, the first element, and you try to put that first element, right. Basically, when you pass the entire list here, the sort operation, the sort function you have written is in the form of what? CIR cons CDR, right? So if you could have sent the list of, let us say, 10, 8, 15, let us say 30, 13, okay. So if I have, let us say, these elements been passed to the list. So how they are going to be represented here? A cons x. A means 10 here, then cons, then you will have x is 8, 15, and 13, right? But then the code, if you see, this is how the list is going to be sent inside the code, because since it was not null initially, when it is null only, then it returns null now. So since it was having elements, so it goes with this particular option. So where it has been represented like this, a colon x. After that, when it has been sent inside the code, you can see that this sort function, which is being recalled here, right? The two-way recursion. This is said to be two-way recursion. You have left recursion. This is said to be left recursion, and this is said to be the right recursion. So see the A element. A element is nothing but the first element. Is nothing but 10, right? So 10 is placed in such a way that the values less than to it, right? Values less than to it will be available in the left half of the array. It means what are the left lesser than 10? You can find 8. So you can find that in the left half of the array, right? And you can see here on the right side of A, in the definition of the code, you have seen that all the elements which are greater than A will come to the right side of the same, right? So here you have what? 15 and 13, right? So that way it comes. So basically in quicksort, what we do is you choose the pivot element and then you place in such a way that the lesser than the pivot will be shifted to the left half of the same, and greater than to it will be shifted to the right half of the same. And you again apply the sort algorithm on the left list and then right list, right? So that's how it's going to be repeated until the entire list is sorted, right? So you can see here, when it is called for list, when it is represented in the form of A cons x, how is it going to be represented? 8 cons nil, right? Yes or no? You don't have remainder part. So this has to be placed in the right position. It means after placing it, you don't find any values which are less than to it will be in the left side. So it will be null here, and on the right also it will be null. So it is just 8 here, right? So when there are no elements, then you don't probably call it again other. So then for right recursion, when you go with, you can see it is represented in the form of A cons x. It means 15 cons 13. But then what happens when it is being sent inside the code, that 15 is going to be placed in such a way that the values less than to it will be moved into its left position. So you can see 13 will be moved, and right you don't have any greater element, so it will be null here, right? So then what happens again? The left will be sent inside. When it is sent inside, you can see that it is represented as again 13 colon as null. 13 colon null. So then this A will be placed on the right position, and then on the proper position. By putting it in the proper position, you shift all its lesser elements to the left and greater elements to the right, but you don't have any lesser element and you don't have its greater elements. So you can find that these elements how you find in the list having been sorted with the logic that we have defined for quick sort. Okay? So this way you can probably write in a very simplistic manner. You can see the code is very simple. Yes or no? If you probably compare it with your C, you may have written it in C++ rather, right? So the code which you have rather written, maybe you have written both iterative versions and recursive versions, fine. But both, if you see, they are implemented with a lot of complexity from the user's point of view as well, right? So from user's point of view, if you can see, they are very easy. Yes or no? What user has to write only couple of statements, nothing else. The rest all being taken care by the interpreter, the language compiler. Fine. Now coming to lazy evaluation, this is another advantage which Haskell is having as one of its features, right? It means that you don't need to process the operation on all the elements. Only for restricted values you will be tweaking and then processing on it until you get the result. Though the list is infinite sometimes, right? So that's how the advantage. You probably see an example here. A language is strict if it requires all actual parameters to be fully evaluated. A language is non-strict if it does not have the strict requirement, right? Non-strict languages are more efficient and allow some interesting capabilities like infinite list. So if the languages are very strict, then probably the list of elements or the inputs that you have to give is required to be very confined. Fine, you cannot give infinite list. But if say language is having a provision where the users are allowed to non-strict, he can probably give any infinite set of element, but the language will take only certain inputs out of it based on the requirement. Then the wider range of inputs can be rather given to that kind of option. You can probably see it in Haskell with the help of this lazy evaluation. You can see here, for example, if I want to find the positive numbers, positive number 0 dot dot. If you say 0 dot dot means if you don't specify the last element, it is infinite kind of thing rather, right? So it finds all the positive element, but then you can restrict it if you want rather, right? For example, if you want to find the square of let us say number. So if you want to determine whether 16 is a square of a number or not, how do you basically define? You have to start checking for all the numbers like 1, 2, 3, 4 and up. You take all such natural numbers and then square it and then compare it with 16, whether it gets equal or not, rather, right? So here you don't get equal, here you don't get equal, here you may get equal. So once you get equal at some place, rather, right, you can stop doing the entire remaining process, right? So that way you can probably able to here restrict the programming from by giving the proper code, but at the same time the list which you are going to give is an infinite kind. I said 0 dot dot. 0 dot dot in the sense starting from the value 0 as an input, you can rather continue till up to infinite. So all such n values you can take and then find the square of the same and then compare it with whether it is equal to 16 or not. When you get it equal at certain point of time, you can simply stop the same. Right? Infinite list will allow you to go with any input to be checked. It means it becomes more generic rather, right? Member functions. Okay, you can write it as like this. You want to check whether a particular item is belonging to the list or not. Initially, if the list is null, then you say it is false. Otherwise, you represent the list in the form of car cons CDR or cons CDR, right? And you take the first element, that is the car result, or the head part, or the first item of the list. It is going to be compared with the B that you have passed, right? If it is equal, then fine. Okay, you return true. Otherwise, you will be calling the same by passing the remainder part of it, right, as the list. To check whether B is available in the remainder part or not. Right? That way it will be repeated, right? So you can see the code is very much simplified with the help of this pattern matching approach, right? So this can be written, the interpretation of the same here. Coming to applications of functional languages, this, as I said, is used for artificial intelligence, knowledge representation, machine learning, natural language processing, modeling of speech and vision. So a lot of applications. Basically, the kind of applications in nowadays which are rather happening, all such AI-based machine learning or deep learning or data science. These all you can probably implement it with the help of this functional programming language in a very effective way, right? But then we got initially Lisp was functional, but then it has been improved to imperative, and then object also been added. Now new languages have come up, and which are providing you with all these features, and they are being invented in such a way that which are quite compatible with the internet as well. Like for example, Python, right? Which comes up with a good handy libraries which probably help you out in implementing all such kind of applications, right? With respect to different domains, the libraries are prepared and they are made available as part of the program, where you have to just invoke the algorithm and then get it implemented. You have all these features that you have in functional languages in Python, like list, data structure, and all list operations you have. In addition to that, imperative programming language features also, like conditional statement, control statement, all that you have, and and you have data type. It's a typeless also, fine. You have type function is available. Of course, the next that we're going to see. Now, when you compare the functional and imperative programming language, I said imperative languages are efficient from execution point of view. But the semantics and syntax point of view, they are quite complex because from user's point of view, user have to write bulk amount of code and all. Concurrency has to be programmer designed. Programmer has to design the concurrency. Whereas in functional language, we see the semantics and syntax is very simple because the code which you have to write is very less and more readable kind of thing. But execution is inefficient because, as you say, as we have seen, there are certain, programming, concepts which are being taken and then implemented by its respective compiler or interpreter. Like for example, tail recursion, if you see, right? So all recursive programs are being converted into tail recursive, and then they will be implemented. So conversion of this will take some time, and then the execution point of view, if you see, since it is interpreted, most of the functional languages are interpreter based. Interpreter based languages are generally slower because the execution of the interpreter based language is going to be done line by line. And another thing is we have some features like tail recursion, where the conversion of normal recursion to tail recursion to take place, for which also again some extra overhead is needed. So that way, if you see, the execution is inefficient, but the programs can be automatically concurrent here. That is another advantage we can probably find. Now, just taking a review of what we have discussed in functional programming language as a summary. Functional programming language use functional application, conditional expressions, recursion, and functional forms to control program execution of imperative features such as variables and assignment. So you don't have most of the time variables or assignment. You will generally define typeless data as well, and you generally just define the code without having the condition to be checked by using proper notations. Okay. Lisp began as a purely functional language and later included imperative features, as I said, right? Scheme is a relatively simple dialect of Lisp that uses static scoping exclusively. Fine. As I said, static scope is the block in which that variable is declared to be used within itself, rather, right? Is what the static scoping is. Common Lisp is a large Lisp-based language, right? ML is, of course, we have seen, is a static scope and strongly typed functional language, which includes type inference, exception handling, and a variety of data structure and ADT as well, right? And Haskell, we have seen, is coming up with a good feature called lazy functional evaluation that gives good support for infinite list and set comprehension, right? Where the programs can be made more generalized and the inputs to be given to that particular program of any kind, right, without having any restrictions on it, rather, right. Purely functional language have advantages over imperative alternatives, but the lower efficiency on existing machines architecture has prevented from enjoying widespread use, right. If you see, as we have seen in the entire chapter, that the functional languages have very good advantage over the imperative alternatives, right? Imperative programming language. But the efficiency point of view, when you have seen, it is lower, because one thing is it is interpreted based. Another thing is, as I said, because of its features itself, extra overhead is needed. For example, tail regression. Because of these reasons, unless the machine is high computing feature equipped with, you cannot probably implement. So actually, if you look at AI concept was in peak at around in 1970s, and those times the languages which are being used to implement AI concepts are Lisp and Prolog and all kind of thing, right? But then, as you have seen, from efficiency point of view, they are lower, and the kind of machines we have that time are not what we have today, rather, right? We've got now, high computing machinery with dual core, octa core, hexa core processors, and lot of parallel processing approaches with pipeline concepts being embedded in at different levels, like having the multiple function units, multiple functional units of subunit, and all kind of. So with having lot of pipeline approach and SIMD and parallel processing approaches, we could see that throughput of the system has been increased to a larger extent. So even such kind of languages also could have been made more efficient on this machinery. Since the time when that was on peak and the kind of language were available were not compatible with the hardware resources that we had that time, so because of which that did not take off as what it was expected to be. But now, as we have got at the hardware in high computing machineries, and efficiency we have increased to a larger extent, throughput we have increased to a larger extent. Now, these AI-based kind of language also have been improved over the time from 70s. If you see, some of such like our tool, and we got tools also now, not required to have to kind of programming for a particular. You can just drag and drop such kind of thing. The code which is associated with the particular respective, what do you call, tools will run behind and then provide you your respective desired output over there, right? So that way, the software point of view and hardware point of view, lot of advancements took place, and because of which another reason this AI have become a reality now.